Hi students, now in this video we'll learn about the first order reactions, right? We'll see the kinetics of a first order reaction. In general, when we have a particular reaction, suppose the reactant A is changed into the product, and for example the order of the reaction is n, so we write down the rate of reaction is equal to k into a power n, where n is the order of a reaction. But for a first order reaction, we know that n is 1, and when you have a first order reaction, so that n is 1, therefore the same equation can be written as like this: the rate of reaction will be equal to k into concentration of A, the reactant A, power 1 because the n is 1 here. This is the first order reaction, and the rate of reaction means we express it in terms of the change in the concentration of reactants. So I can write down the reaction like this. The change in, say, minus here is a decrease in concentration. The negative sign, it shows with time the concentration of A actually decreases. So this is the rate of change of concentration, right, of A. So decrease in the concentration of A by change in concentration of A by change in time, that is equal to the K into concentration of the reactant A. And if we separate the variables here, if we take the concentration terms to the same side, and you get the k dt delta t, and then let's integrate it between the two limits, between the two values from 0 to time t. Okay, so from 0 to time t, so that initial concentration is A naught, and after time t the concentration left is AT. Suppose we have the when we start with the reaction, A changed into the product, and when the time is 0, at that time the concentration of A will be written as A naught, right? The concentration of A is A naught, and after time t, when the time t seconds, after the time t seconds, or let's suppose this is 5 minutes, 10 minutes, whatever it is, so the concentration left is AT, right? So between these two values here, when we integrate it here, this equation, what you get the ln of concentration of initial ln initial concentration by concentration after time t is equal to kt, or you can write it like this also. Okay, fine. So or we can also write it like this. Suppose you want to find the rate constant k for this one, for the first order reaction, that will be equal to 1 upon time ln of initial concentration of the reactants and divided by the concentration left after time t. Okay, this is the rate constant k for the first order reaction. Okay, let's elaborate it a little bit more. Suppose we have a reactant A, it changed into the product, and when the time is 0 at the start of the reaction, let's suppose we have A moles of this, the reactant. Okay, at that time the product will be 0, correct? After time t seconds, right? Okay, after time t, so x moles of the reactant A have been converted into product. Now the number of moles left after time t will be A minus x, because x is the number of moles that have been converted into the product. So therefore you can say, now this is the concentration actually after time t, and this is the initial concentration. Okay, so therefore I can write down the same equation, the previous equation that we have written like this: 1 by time into ln of initial concentration at the start divided by the concentration after time t, right? So I can put the value here like this: 1, so this is the 1 upon time, right? Okay, this is 1 upon time into ln of initial concentration A divided by A minus x. A minus x is the concentration left after time t. Okay, so how we can further write it like this: k will be equal to 2.303, when we change the ln into log. Okay, so divided by k into log of initial concentration by concentration after time t. right? This is the equation that normally we use to solve the question. This is the rate constant K for the first order reaction, which is equal to 2.303 by K log of A by A minus X. Okay, fine. So we can use this particular equation, later on to solve some of the questions. Okay, so this is actually this is the time t. Okay, this is 2.303 by time log of A by A minus X. Or if you know the rate constant K for the first order reaction, you can find the time actually, right? If you know the K value, you can also find the time for the reaction to get completed up to some extent, right? Suppose you know the time, you can calculate from the rate constant K if you know the initial concentration and the concentration after time t, right? So you can find the time taken by the reaction to get completed. Okay, now there is one more term that is called as half-life period. What does the half-life period of an equation mean, of a chemical reaction means? Half-life period basically means the time taken by the reactants to get converted into the product, right? How to get half of the reactants converted into product, right? So it is, suppose if we have the initial concentration of the reactant A changed into product. Suppose we start with A moles, right? Okay, A moles, and half-life period means time taken by the half of the A reactants to change into product. So that reaction is actually 50% completed, right? Or sometimes we say the time T 50%, time taken by the reaction so that the initial concentration becomes half, right? So that half of the reactants convert into product. Okay, so this is the time T in which the initial concentration becomes half. And how we can calculate it? Again, we can calculate the half-life period for the first order reaction from its rate constant K value. Okay, we know the rate constant K for the first order reaction is 2.303 upon time log of initial concentration by A minus X, right? This is A by A minus X. This is the rate constant K for the first order reaction, and from this particular equation I can find time taken by the reaction to get 50% completed. I can find the time T 50%, right? Okay, or you can say T 1/2. Okay, so you can find it like this. Suppose it will be the 2.303 here by K, okay, log of A by A minus X, right? A minus X means what? This is the concentration left when half of the reactants have been converted into product. So therefore, when at T half, 50% of the reactants have been converted into products, therefore the amount left will be again A by 2, right? So now at T half, the A minus X is what? It is actually equal to A by 2, correct? Okay, so I can write like this. So I can write it also like this: 2.303 by K into log 2, and log 2 we know it is actually equal to 0. This log 2 is 0.301. When you multiply this log 2 value, which is equal to 0.301 into 2.303, so you can find that, you can see that T half will be equal to 2.303 into 0.301, which is actually equal to 0.693 by K. So here we got, this is the half-life period. This is the time taken by the reaction to get half of the reactants converted into the product. And we find the T half, the half-life period for the first order reaction, it depends on the K only, right? So K, the rate constant K factor only. Okay, if the rate constant K is high, the half-life period will be less, because rate constant K tells us about the reaction rate. High K value means the reaction is fast, so therefore the time taken for half of the reactants to get converted into the product, that will be that will be less, okay, if K is high. So it is inversely proportional. So one more point we can get here, that half-life period does not depend on the initial concentration also. Very interesting here. For the first order reaction, the T half does not depend on the initial concentration, right? Does not depend on initial concentration of reactants, right? Initial concentration of reactants. Now let us discuss about the zero order reactions. A zero order reaction, we know here the concentration, here the rate of reaction does not depend on the initial concentration of the reactants. So that means even if you increase the concentration of the reactants, you know, the rate of reaction will remain same. Suppose we have the reactant A, it changes into the product, and since the n is 0 here, okay, so I can say the initial concentration power 0, rate of reaction is equal to K into initial concentration power 0, because n here is 0. This is a zero order reaction. So we can further write it like this, that means minus change in concentration of A delta T, that is equal to this one, K into initial concentration of the reactant A power 0, okay, or I can write it like this, minus change in concentration of A by delta T will be equal to K, right? K only, because here this term is 1. Okay, so I can now separate the variables and I can write down this particular equation like this, minus change in concentration of A will be equal to KT, okay, K delta T, and then we can integrate the two terms between the two, we can integrate it between the two limits from time 0 to time t, right? From time 0, from the time 0 means from the start of the reaction up to some time t, when some after 10 minutes or 15 minutes or whatever is that, correct? Suppose we start a reaction at the after 10 minutes, what will be the rate of reaction, correct? So between those two time periods we can get the equation like this. If you integrate it here, so you integrate it between the two limits when the initial concentration of the reactants is A0 and the concentration left after time is AT. Okay, I'm going to integrate it. So what I get, you get this one, initial concentration minus concentration after time t is equal to K, rate constant K into time t. Okay, or you can further modify this equation, rate constant K will be equal to initial concentration A0 minus concentration after time t by t, okay, by time. So this is the rate constant K for the zero order reaction. Okay, this is the equation for the zero order reaction. So rate constant K is equal to initial concentration minus concentration after time t divided by the time. Okay, so now let's find the half-life period for the zero order reaction. As we know, the half-life period is basically the time, right? It represents the time in which the initial concentration of the reactants become half. So that means it is basically the time taken by the reactant molecules to get converted to it is half. Okay, so that half of the reactants convert into the product. If you start, suppose, a particular reaction with 10 grams of A, so the time taken by 5 grams to get converted into the product, that is the half-life period. And we can find the half-life period from the rate constant K value here. We know that this is the initial concentration minus concentration after time t is equal to KT, or we can further write it like this. I can write it, K will be equal to initial concentration of reactants minus concentration after time t by time here. Okay, so when let's suppose here we start the reaction with the A moles of A, and when the time is t half, how much of the initial concentration will be left there? That will be A by 2. Okay, that will be A by 2. So this is the concentration left after half-life period. So when I put the same values here, I can find the t half. From this equation, first let me write the K time t will be equal to initial concentration minus concentration after time t by k here, which will be equal to, when I find the t half, when I put the time t half of the reactants have been converted into products. So I can write it like this: A minus, okay, so let me write it over here like this, right? Okay, if I take it k into t half like this for the simplicity, okay, this will be A minus, then it will be the concentration will be, it will be the A by 2 right here, okay, it will be A by 2 over here. Let's erase this particular area first, okay, right, rub it, okay. Now this is the A by 2, okay, when we put it, this is the 2A minus A by 2, this will be A by 2, right? So this is the initial concentration by 2, or we can put it, we can put it like this: the half-life period is what? That is A by 2k, right? That is A by 2k. So that means this is the initial concentration by 2k. So half-life period here, it is directly proportional to the initial concentration of the reactants. So if the initial concentration of the reactants is more, so half-life period will be more. Here the T half in the zero order reaction is directly proportional to the initial concentration of the reactants. But for the first order reaction, we found that T half half-life period of the reaction does not depend on the initial concentration. So that remains the same for the first order reaction, but for the zero order reaction, it is directly proportional to the initial concentration of the reactants. Okay, so hope you got the concept. Thanks for watching the video. Bye.